Good evening, everyone. Welcome to today's problem solving section, course Digital Design with Verilog, week 8. So today we will see the sequential circuit and the Verilog code. Yes. So and the Verilog code for the sequential elements such as flip-flops and latches. So the first main difference is between the sequential and the combinational logic is the combinational logic output depends on the input and it does not depend on the previous output. So it just depends on the input. So if we have A and B, so the output depends on A and B. And if there is some the combination circuit, every gate, every transistor will have some delay. So it will have a respective propagation delay. But it does not depend on this F. Whereas if we go for sequential elements, output not only depends on the input but also depends on the past state. So we have the H, which is the history or the sequence or the state, like the past state. So there is a feedback between the output, sequence, and the combinational logic. So for the sequential, it is F, which is depends on output. F depends on the A input with respect to time B, B input with respect to time T, and the H, which is the previous state or the history or the sequence. So there is some memory. Whereas for the combinational circuit, it depends just on the A and B. If okay, this is Y, so I will take Y, and I want to write function of, and if the output is Y, then the function of A and B. Okay, so we want to store a particular 1-bit value. That means, for example, if you want, if you press this button, it should be storing 1, and a particular LED should glow. And if you press this, the stored value should go from 0 to 1. So, like this, if it is the requirement. So, we need a feedback. Can this feedback help for a storage? So, this can, if for example, if we have a 1 here, the output is 1. Again, this input is 1. So, if we change this S to 0 also, we cannot change this value. It is getting to a, like we apply S to some value when we power on, and it is at the stable state. If you start with 0, you apply initially 0, then the output will depend on this value. If it is don't care, it will depend on this value. And if we apply 1, the output is 1 always. So this cannot be used as a storage element to store as 1-bit data. So if we consider an example here in the waveform format, it is shown that S and T depends on the output. So if this goes to 1 with the delay, output also goes to 1. and Q goes to 1 with this much of delay, and because this is 1, so the T is also 1, and it remains in the 1 for ever, whatever value of the S is applied. So it cannot be used to store a single bit because we cannot store now apply a 0. So next we have a cross coupled OR gate which can be used to store, also set and reset the values. So if we observe here, um, if we have R is equal to 1, S is equal to 0, this one here, it's an OR gate. So the NOR gate truth table. So this will be 1 and rest of the bit 0. So any one it's 1, output has to be 0. So if this is 0, 0 will come here, 0, 0 will be 1. So output is uh, at 0. So it's in the reset state. So this S we call as set state, and R we also call as reset state. So now when we apply 0, 0, this is to like it's a store state. It will be in the same as the previous state. So for example, if it is 0, 0 and the previous state here is 0, so this 0 will come here. Previous state is 1 here, so 1 will come here. So 0, 0 means again NOR gate output should be 1. 1, 0 NOR gate output should be 0. So it will be maintained in this state and like storing this state value. And next state, if we have 0, 1, that is, this is the set state and this is the reset. So any one of the input is 1, the output should go to 0, and this 0 comes here, so 0, 0 is 1. So in this state we observe that Q is set to 1. So it's a in the set state. Now again if we apply 0, 0 and this 0 is 1, this 1 comes here, this 0 comes here, and it maintains the same state. And in the waveform format, again if we see here, the reset is 1, that means output should go to 0, and here the set is 1, that means output should go to 1. And next, so these are the inputs and these are the next state values. So 1, 0 means it is set, this is store, this is reset, again store, and this state is not allowed. Let's see why. If both the inputs are 1, 1, if we have a NOR gate, again just so any one of the input is 1, so output should be 0, and we observe both Q and Q bar is 0 when we apply S is equal to R is equal to 1. But this is not allowed, first because both Q and Q bar cannot be same, it should be complement values. Next we apply 0, 0, which is used for store state. Okay. Now this 0 comes here, this 0 comes here. If we assume that delay of both gate is equal to 0 or same, and input applied at same time, so there is no delay between the input as well as the difference. Both of them are giving 0 at the same time, so there is 0 delay or it is having the same delay. That means 0, 0 should give 1, 1. This one comes here. So it's again 0, 1, which is 0, 0. Now it maintains at the state, the output will be maintained at 0, 0 because 0, 0 if we give. Okay. Now it is again changing. So in this way, we cannot like predict what is the output when we give a value for store. So it is in the unstable state. When both the gate have the same delay or the zero delay and the input arrives at the same time, we have applied 1, 1 state, and after applying 1, 1 state, we give a 0, 0 state, which is a store state. Then we cannot predict what the output will be. And for 1, 1, we are getting the output to be 0, 0. So this is called as the unstable state. Okay, in further, we will see what is the race condition also. Okay, so Verilog code for the SR latch. So the inputs are S and R, and the output is Q and Q bar. So what is the from here? If we take Q bar, it is S NOR with Q complement. Okay, I'll write it again 1 second. So the Q bar is complement of S or Q, and Q is the complement of R or Q bar. This you can name as QB, QB, so that, yeah. So now this we have mentioned it here. So this is the SR function. Now for the test bench, the inputs in the module will be the register here, and the outputs will be wire, and we are instantiating the module SR latch with the latch name, and values are SR, Q and QB, and initial begin. These are the statements to write into the waveform, and these are for displaying. So first we give 0, 0, which is a store state, 0, 1, reset, set, again store, and this is the invalid state. Okay, so this is the output. Like if we give 0, 0, the output is invalid because the previous state we don't know. So the Q and Q bar remains in the invalid state. Now we perform reset, so output should be 0. Here we perform a set, so output should be 1. And after set, it is in this store state, so it is now 1, 1 is an invalid state because both the outputs are 0, 0. And in the waveform, similarly, we can observe what is the S, what is R, and the Q value. So this is the don't care value, and here we get a 0. Now, if we were pressing this button, so it is setting it, so it will give the output 1. And now if you release this button also, it is 0 0 state. Again, it will be output will be in 1. Now, if you press this cancel, it will go to the reset state. Again, if you release the button, that is 0 0 state, it will be in the off state. So in this way, it is able to perform this operation. But what will happen if we press both the buttons together? We saw one condition which was unstable state. Similarly to the NOR, we can have NAND gate also. And for the NAND gate, instead of S and R and giving output Q complement and Q, here S will give Q and R will give Q bar. So NOR gate, R will drive the Q. For the NAND, S will drive the Q. So SR latch with NAND gate, it's like opposite to SR with NOR gate, where set will do Q is equal to 0 and reset will do Q is equal to 1. And 1 1 was forbidden there. Now here 0 0 is the unpredictable output, whereas 1 1 is the stored output. So now the problem of 1 1 is again to see the race condition. So what is race condition is, if we give 1 1, we said for not any one input is 1, the output should be 0. Now, if this gate is performing faster than this gate, then this gate output will come to 0. And for 1 0, output is 0. Say here 0. Previous value was say 1. And this gate is slower, so it has the previous value. So this 1 1 should give the value 0. So now if you change the input, so it's 0 0 now. 0 0, output is 1, and this is faster gate, so this 1 will come here, and this will give 0 1, which is 1. Yes, you have any doubts?
Good evening, ma'am.
Yes, good evening.
Ma'am, I have a doubt regarding the assignment base only.
Okay.
I have one doubt in one of the question of
Uh,
week 8 assignment.
okay. I will not give directly answer, but I can help with the concept or the slide related to that.
Okay.
Yes, please, you can ask.
Uh, Ma'am, my question is that in question number 7, here you have asked that what will be the final value stored in a write shift register if the input is 101101.
Okay.
So, ma'am, after solving that question, I think the option is not regarding to the correct answer. There is no correct answer as per my calculation.
If this is the value, if we perform right shift, then it should be 0 1 0 0. I think this is the concept, right?
Yes, yes.
So this value will be like discarded. If you solve like this and you're not able to get the correct answer, then you can just write it in the Q&A forum, in the forum.
Okay.
Yes.
Thank you, ma'am.
Yeah, welcome. So we said 1 1 is not allowed. So it gives say 0 0 output. Now again we give 0 0, which is the store state, and this is uh, a faster gate, so it gets this value 0. So 0 0 1 it gives directly. Now this gate, instead of seeing 0, it sees 1. If it sees 1, then 0 1 output should be 1. Again this is 1. So 0 1 output is 1. So because of the race condition, its value is like again 1 1 only. Previously we saw it was like at this place we were not able to say what is the value, but whichever gate wins in the way, it is like passing the race condition. So who will win 0 or 1 eventually, and then what will be the value of q? So what is the solution for race condition is like, instead we don't want this 1 1 condition. So if we apply a NOT gate and give here, it will be 0. So that means this AND gate output will be 0. So actually we will not get the 1 1 condition. So in this way we can like avoid this 1 1 condition. Um, we want to ensure that S and R both do not get 1 at a time. But this as a problem with this is that this path has more delay. So problem not just one of the user pressing two buttons at a time. So can also occur even if S and R inputs come from the circuit that supposedly never set to 1, but does due to different delays of different paths. But here the longer path from X to R and than S to Q, this path is longer compared to this path. So will cause S and R equal to 1 1 for a short time. See, for this short duration of time because of this two propagation delay. So again we have the problem of that 1 1. So here in this approach we have a enable signal. So okay, if both are 1 1, whenever enable is 1, we will not be applying 1 1. So only set S and R change when S is equal to 0, such that we can ensure 1 1 does not occur. And once C is changed to 1, after a sufficient time, S and R to be stable. When C becomes 1, then the stable state S and R value passes through the two gates to the SR latch. So here, yeah, this is sensitive to the level. That means whenever the C is 1, then only this gate S will come here, R will come here. And now this path is stabilized. Like we can wait by controlling the C value. Yes. So you have any doubts? Verilog code for RAM. Okay, so it is like memory, and for memory, say we use register. I want a memory which is of 8-bit width, so 0 down to 7, and I want say some 256 memory locations, so 255 down to 0, something like this. Then you can have an address bus, address again of register type. So it should also have able to access 2 to the power. How much is 256? I think 8 should be sufficient. So 7 down to 0 for address. Again, you want an enable signal for read and read enable, write enable. Address should also be an input actually. So you can take this as input ports. So in this way you can define the memory. Is it clear? Um, Logic is we want this number of bits should be 0 to 7. So each is a 8-bit value. So the number of bit value you want, you can specify here. And the values, it is 0th address to 55th address. So now if you get an address, say which says 127, that will be some location here. So this should be given from the input, and what are the inputs we need is the address, and if it is saying read enable, that means the content of this should go to the output, and if it is saying write enable, then the content of the input should come here. So the input port, you should be able to give the address, and address will not be single bit, it will be for us 2 to the power 8, which is 256. So 8-bit address is needed, and then we need a read enable, which says that read or write if I take. Okay, 1 bit also you can take. Read or write. It says say it is 1 means read, 0 means write. And if it is writing, so data also should come from the user. And output, if it is a reading value, then the output should be the read data. And how many bits it will be this data? It will be again 8-bit, or how much bit width you have given here, that much. and output will also be 8-bit because we are defining it. So now inside this, how much memory like you want, that we have to define as the register, say 7 down to 0, the memory, and how many such bits. So with this, we will get the memory which looks something like this. Uh, is it clear? Any other doubts? Okay, so now uh, we have this logic which ensures that we will not get 1-1 state, but because of the propagation delay, we saw that for a short duration of time, the state still goes to 1-1. So we have an enable signal which ensures that we are having that stable value. So the C or enable will wait till the S and R becomes to stable value. And then we have a storage state where this value is getting stored. So in this way, we are able to have a latch which ensures stable and stabilize and stored state. So what is the clock period? So this duration of time is called as the period, and 1 by period is the frequency, and clock cycle is one such interval. So this is for clock signal for RS latch. Um, Whenever the clock, instead of enable, if we keep this as the clock signal, so this duration, when the clock is 0, X and Y state can change. But in this duration, when the clock is 1, we should not change the X and Y so that it will not affect. And so this is operating like at the level of the clock we saw. So at this level, it is doing the process. So it is a level sensitive, and latches are level sensitive. And what will happen if we connect like this to form a shift register? We want one bit to shift right, or say for example, right shift means right shift 1 bit per cycle. But uh, because it is the level sensitive, we have a duration of time. So in this duration, if it is shifting once, again it will shift again because we have a level sensitive. So we cannot connect a latch to form a shift register. That if we have a bigger clock, then multiple shifts will happen in the same level. But other solution is that we can make the clock to be very small so that only one shift happens per the one positive level, because it's a positive level sensitive latch. That is, we are trying to make this edge operate the flip flop at this edge. So that is called edge triggered circuit, and that is called as the flip flop. So we want, if it is a rising edge, this is the rising edge, or the in Verilog we will call this rising edge as pos edge. So generally like the latches are level sensitive storage devices and flip flops are the edge sensitive storage devices. Uh, Latches are like transparent for that complete level, and flip flop is like opaque and when it only operates at the particular edge. So value get changed only at the edge of the clock. Master slave D flip flop, two latches, output of the first goes to the input of the second. So we have a master latch and the output of this goes to the input of the second. This is the master and this is the slave. And we have a clock. So when this is functioning, this should not. And similarly, when the slave is working, master will be in off state. So master loaded with when C is equal to 0, then servant when C is equal to 1. When C changes from 0 to 1, master disabled, servant is loaded. So you can see this. Yeah. So this is a D flip flop. D means data flip flop. That is, if we have a D input as say 0, output is 1. Oh, sorry, this is not toggle. D is output is 0, and when D is 1, output is 1. So now if we see this waveform, mm, the clock is 0 here. So 0 here means 1 here. That means master should be uh, operating. And if the data signal input is this given to the master, so the DM, so QM we have to see. So the clock will be with the not of this one. So it will be 1, then 0. So we have a slight delay here, propagation delay. Then what will be the output? This complete duration, this D value should come to the output. So we have a slight delay here and the output comes till here. Next, this edge CS is 1. So CS is 1. This servant clock is 1. That means this value should come to the output. So this 1 should be appearing here. And now if you see the waveform of a clock, this is the clock. This is the positive clock. Somewhere here we are able to observe. Okay. So in this way we are making the level sensitive latch to the positive edge triggered flip flop. Now if we want to make negative edge trigger, we have to just give a 0 here and a 1 here. I mean not gate will come here instead of here. So if you see the servant is working in this edge, that means this will be the final flip flop. So this is the rising edge and this is the falling edge. So the Verilog, this is used to indicate the posage and negate. This is for the rising edge and for falling edge negate. Now, if we connect multiple such flip-flops, this consists of master-slave combination, master and slave. So now it is a edge triggered. So whenever we represent D and Q, this is like latch, and whenever we put this symbol a triangle, this indicates it is a flip-flop. It will be operating at the edge, not at the level. And if it is with a bubble, this indicates is a negate flip-flop, and this indicates is a posage flip-flop. So we have seen like latches are level sensitive and flip-flop is edge sensitive, and that is like we can have it rising or falling, that is posage negate. And this is the positive edge triggered D flip-flop with optimization. So the this signal, which is the enable, which is the clock now, and the complementary goes here. And when we have S and R, we connect like complementary values. It is the D flip flop. So this consists of total 4 NOR gate, 4 AND gate, and 2 NOT gate. So the Verilog code, this means the this one always at the rate, and this list is called as sensitivity list. So any value changes in the values listed in this list changes, then the output will uh, change. That means this values will start to execute. That is, this values in the begin and end will be starting to execute. And if it is asterisk, like it's always going to be executed, so it's almost like equivalent to it's going to be always executed. Now we said that if the enable signal means if the enable signal is 1, then the output is D. Uh, if you want, you can also mention else, that is enable equal to 0. We want Q to be okay. Q is already a register, so okay, we can write 0. Or no, we want to maintain it, so we can write Q is equal to okay. Okay, fine. No, just yeah. So whenever the enable is equal to 1, we want the output of Q to be the D value. And then we connect it in the master and slave combination, where master gets the complemented clock and the slave gets the normal clock, and D is the input, W1 is the output. So W1 is an intermediate output, that is, this is the master, this is the slave. We have a clock which is connected to the slave, and the complementary clock is connected to the master, and D, Q, D, Q, So this value we are storing in a wire. So we have wire W1 and we have Q bar also. So Q bar is just the complement of Q, and the slave latch we have the input Q, W1, output is Q. So in this way we can design a master slave D flip-flop. So for the test bench, we are instantiating the D flip-flop, and for passing the values, first we need the clock. So we are generating the clock for every 10 unit of time. We want the clock to toggle, and initially clock is 0. And we can also display the clock. Then we want the values of D to be 0, 1, 0, 1 with some specified unit of delay. And this value we are storing in this file. So the waveforms can be observed there. Like this is the D value, and this is the positive edge. In this edge, we observe that output is changing to 1. Here again, output is 1, so it remains in 1. Here it is 0, so it goes to 0. Okay. So next slide. Yeah, for the SR latch, further optimized design can be using this NAND gate. So it just requires some 6 NAND gates. So I'll just skip it. This is just the optimization of the D flip-flop. So it just requires 6 NAND gates. And this is the transistor level circuits and its optimization. Okay. This is convention, that is circuit is set means set indicates output is 1 and reset indicates output is 0. So flip-flops have two outputs, 0 and Q and Q bar. So due to the time related characteristics of the flip-flop, QT and Q we call as present state, and after applying it goes to the next state. So like okay, for SR we said that when we apply say 0 0, okay, for 0 1 it's going to the reset state. So Q and Q bar are in 0 1 state. Next we apply 0 0, that means it is in the memory state, that is the previous. So this is the next state, and this is the for this next state, this becomes the previous state. So that's why we have present state and next state, or present state of and previous state. Any convention can be followed. And SR is a set reset flip flop, and D is called as the data flip flop to store a single bit of data. JK flip flop, this condition is removed, and this condition in JK means toggle, where a bit it can be toggled, and T flip flop is a toggle flip. So JK flip flop can be designed from the SR flip flop. With this one is the enable we saw. Now we just need this feedback going to the J and this feedback going to the K. And its characteristic table. So this one we call characteristic table. Actually, we have two types of tables. Characteristic table is the table which represents between the input say J and K. With respect to the output Q. And we can derive the equation. So this is called characteristic equation. And the next one, it is called excitation table, where we have, say, the next state, present state, and what will be the input, say J and K. So these are the input and this is the output. Yes, so I hope these terminologies are clear. And when we are doing some flip-flop conversion, again we will be using these terminologies: characteristic table, characteristic equation, and what is the excitation table. So the one is representing here is the characteristic table, and this one represents the characteristic equations. So how it is? Okay. So for the master slave combination, we need this feedback coming to the J from the S output, and this feedback coming from here. And again, the same way, the clock and the clock. This is the clock signal. So here it will be the clock complement, and the slave will get the clock signal. And this will be remind the J and the K input. So in this way, we can get the master slave JK flip flop. And to synthesize the D flip flops, okay, simply set K equal to the complement of J. And for like the JK flip flop is a universal flip flop because it can be configured to work as any flip flop. Like T, if you want to toggle, you can see if it is 1, that is the T input, the output will toggle. So we want to connect both together so that if it is 0 0, it will remain 1 1, it will start to toggle. Next, D flip flop, that is whatever is the value. Say we assume this is the D and this is the complement of D, then this becomes a D flip flop. SR flip flop, anyway, this state is not allowed. So till this state, if we allow, it becomes a SR flip flop. So the Verilog code here, we are using the switch statement to define the different states. So this is the concatenation operation, and we are combining, like concatenating J comma K, two values. And now if it is 0 0, we know Q, the next state should be the same state. And this is called the non-blocking assignments, which is commonly used in the sequential circuit. And if it is a combination, then we will use this one, which is blocking. So this is okay. So 0 0 we want the same state. 0 1 we want it to be reset. 1 0 we want it to be set, and 1 1 it is the toggle state. So complement of Q. So these are the 4 case values. If you want, you can write the default case also. And to end the case statement, it is end case keyword. And now this function will be working only at the passage of clock. So if you write it, it will be synthesized as a flip-flop. Next, we are instantiating this module and the module name. So first we want to generate the clock. Next, this is for the waveform, and we are giving all the 4 combinations that we can apply to the JK. So I hope this form is understandable. Like, I'll just give some 2 minutes. Okay, so at the starting, when both are 0 0, without the previous state, memory state, we cannot say what it is, so it's a don't care. And also the clock, this passage has not come still. At this passage only we have to see what the value goes. So it is 0 1, that is reset, so it is going to 0. So it's a positive flip-flop. So next positive edge is 1 0. So that means it should go to 1. And at this positive edge, it is 1 1, that means it should toggle. The previous value was 1, so it goes to 0. Okay. Next, to design a toggle flip-flop, we said that we will connect both J and K. So what is T? If it is 0, that means J and K value are 0 0. That means Q is the next state, Q is the previous state. One top, and this will be 1 1, which is Q complement. So we update the toggle state. So the Verilog code for the toggle flip-flop, that is here again. Now we will use a ternary operator, and this is This assignment statement is a non-blocking assignment, and this one is the ternary operator, which means, so now we want the output to be, if this value is true, that is 1, we want output to be the complemented value, toggle. If it is 0, we want the same value. And now, and this should work at the positive edge of the clock, so because it's a flip-flop. So 4 types of flip-flop. This too, if we consider from the SR, it is the D flip-flop, and this too from the JK, it's the toggle flip-flop, and this too is the D flip-flop. Toggle is not possible because this value is not allowed with the SR. Okay, given a D flip-flop, how to construct a JK flip-flop? So there is one method given in the slide. Okay, at the end, we will discuss one more method. So I'm just skipping it. So what is characteristic equation? It is a description of the state, next state table of the flip-flop, constructing from the K map. So uh, so we said, what is the characteristic table? It is the table where we say what will be the next state with respect to the input. And what is excitation table? We give the present state, next state, and for that what will be the input. That is known as excitation table. So the characteristic table for GK flip-flop is given 0 0 means store, 1 1 is toggle, and it is the reset, and this is set. For toggle flip-flop, when it is 0, it is same value. When 1, it is the toggle, and D flip-flop, it is the same. The same means it is not like D is equal to Q. Whatever D is there in the next clock cycle, Q will get that value. And characteristic equation. So for this, if you want to derive the characteristic equation, say Q plus, we have Q's T when J is equal to 0, K is equal to 0, that time it is Qt plus 0. So if we write J bar K and 0, that means it is going to be 0, so we can leave that, and then J K bar Q is 1, so it is 1 plus, when it is J K, it is Q bar. So this is this equation. Now if you same, actually this T is not there, and this is same value. Here we are multiplying it with Q bar plus Q. And from this two terms, if we take K bar Q common, J plus J bar, and from these two terms, if we take J Q bar common, then we get the output as K bar Q plus J Q bar. We can also use K map for the getting this. We can also write characteristic equation. So here it is directly plus is D, and this is complementary. So how we will write dq plus, it is 0 means t bar, it is qt plus, when it is 1, it is qt complement. That is, it is complement XOR of qt. Next, so yes, in this way I said that we can use the K map for uh, getting the characteristic equation. So we said 1 is not allowed. So we have a don't care, and this don't care can be used for simplification, and we get this as the characteristic equation. Next, flip flop with asynchronous input. What does this mean is, we have a flip flop, we have an input which is varying with the clock. Like whenever the clock positive edge comes, the flip flop is operating based on the input and the previous state and giving a particular next state output. Now, if we want some of the inputs to not depend on the clock but directly affect the output, say preset. So if I just press the preset, I want the output to be 1. Clear, that means if I press the clear, I want the output to be 0. That is like direct set and direct reset without waiting for the positive edge of a clock or without waiting for the clock. So such inputs are called as asynchronous inputs. So we assume that when preset is high, okay, so if it is not mentioned, like we assume that preset, if it is active high, that is it is 1, then we want immediately Q to be 1. And when clear is 1, that means we want the output to be 0. And when both preset and clear are low, we want the normal flip-flop operation. So if we have a JK flip-flop with active low, preset and clear inputs, that means whenever the preset is 0, we want the output to be set to 1, and whenever the clear is 0, we want the output to be set to 0. So in this, when both are 1 1, it will perform the flip flop operation. And if this is JK flip flop with J equal to K equal to 1, that means it is in a toggle state. So it's a flip flop at the positive edge. Whenever the positive edge comes, 1 becomes 0. Again at the next positive edge, it becomes 1 and 0 on the next positive edge. So any doubts in this waveform? So if we connect a group of 4D flip flop, say we have 4 input data, it's like forming like a register, and we can observe that this is I0, I1, I2, I3. This data is coming here. This data is 1. This data is 1 and it is going 0 here. And this data is 0. So it is 0. Whereas this is 1. So it's going to 1. in the next cycle, this maintains at 1, so it is maintaining at 1. But whereas this one, it is going to 1. So you see this data is 1, 1, 0, 1. So at this positive edge of the clock, we get 1, 1, 0, 1. At this positive edge of the clock, here we have data. This is also 100. So we have 0, 0, 1 and maintaining it. Okay. So in this way, it is acting like a shift register. At the positive edge, it is shifting 1 bit of data. But here, if I have a clock like this, say clock, I have a D input. We have a concept called, at this edge, we want the data. So we will not give the sharp data like this. Okay, so we have a concept called as setup time and hold time. Setup time is the amount of the duration of time, amount of time we want the input to be stable, and hold time before the clock, and hold time is the duration of a time we want the input to be stable after the application of a time, after application of a clock. So we want a one data to be at the output. We keep it stable for a setup t setup time plus t hold time. Then only it will be like, we cannot, here is a clock and here is the data change, and we cannot expect the output to change based on this value. Yeah, because setup time has to be met, and if it is not met, then the output may go to metastable state. The output will not be uh, at a predictable state. So the Q value, so this duration of time we call it as setup time, and this duration of time we call as hold time. And there may be some delay. So after the clock, it may take some time, say this much, and the output goes to 1. So okay, any doubts? So the Verilog code for this register, so if we assume that we want a 4-bit data, So we need a clock, and say it's enable signal and 4-bit register, so 4-bit input and 4-bit output register. So it's a reg type, and in between store values, so 4-bit stored. So if the at the positive flow, if we enable it, we want the stored data. Stored data is this one to be the input data, and at the always at the positive edge of the clock, we want the output to be the stored data. So in this way, we can get a 4-bit register. So it's like now the Verilog code for the register, I mean the test bench. So we define the inputs as the register and the output as the wire, and we are generating the clock. So next is we are applying different values with a certain delay. Okay. So registers with parallel load, that means whatever is the content here, we can parallelly load and we'll go to the output. So now if we want to load it, that means if load is 1, that means it should enable this based on the clock signal. The input will go to output. Like what will be the logic design for this load? What will be the circuit for this load? That only we are trying to analyze. So if the load is 1, we want the data to go to the queue, and if load is 0, we don't want that to uh, disturb the output. So it should be the previous output. But one option is that we can mask the clock when the load is 0, so that the clock will not go to the flip-flop and automatically the data will be the previous data. And the clock will be applied only on the load. But in this way, we are adding a logic gate in the clock path, and which is not a good design to modify the clock path. So what is the other method? So we need a multiplexer. Multiplexer is say 2:1 multiplexer 0 1 based on the select line A B and say O. So A B okay, I think I'll just take that based on the select line, and this is output. If the select line is 0, output will be A. If the select line is 1, output will be B. This is the operation of a 2:1 multiplexer. Now, if the select load is equal to 1, that means it will be selecting I1, which is the data parallel input data. Whereas if it is equal to 0, it will be selecting I0, which is the A3. Means it is performing the store operation. And we are not modifying anything in this clock path. We have not added any other combinational circuit. So shift registers, register which consists of a set of flip-flops, and 4-bit shift register. We have seen an example. So other we have serial in, serial out also. Okay, so what is the right shift example? Like we want moving each bit one position to the right, and if and we add a 0 to the leftmost bit, that is the input whatever rest is. For example, if we are shifting 0 and we perform the left shift operation, one bit it is moving to the, okay, this is the right bit operation, this is the right shift operation. So next clock cycle, it will move one more bit right. Next clock cycle, one more bit right. And the next clock cycle, this one will be discarded. And every time, the leftmost bit is assigned to 0. Yeah, so if we have 110, we want to shift this content to the right. That means this bit will be removed. So the new content, shifted content will be 011. So implementation, we have a serial input and serial output. So if we consider a 4-bit shift register with serial in and serial out, that means data will come from here and that last data will go to the serial out and like discarded, or this, like, it's going to the output coming from the flip flop. So if the serial input is 0, 0, 1, 0, 0, 1, Q3 gets this one after one clock cycle. And this one goes here, here, and here. So this is Q3, Q2, Q1, Q0. It is taking 4 flip-flops, so total 4 clock cycles to reach the output. So the next 0 will be appearing here. Okay, so this appears here, here, and one more clock cycle to get the 0. So this is serial in, serial out shift register. And now if we want a shift register with a control signal, that is to allow register to either shift or retain. So for retaining, we need a feedback and I need a shift control. Now we say 0, that is the retain. That means we apply Q to this to feedback. So it is the, if it is Q plus, here we get the previous value of the Q. And this is the serial shifting in bit. So this is the previous output, which is the shifting in bit, and its own flip-flop will come here. Okay, so this is with the control. So we have serial control. If it is 0, then the output remains, and if it in the same state, like it's a storing, and if it is 1, then it performs a 1-bit shift. Yes, so if it is 0, we observe that there is a feedback from the output to the input, and so it retains the previous state and there is no connection of the shifting. Whereas if it is 1, this is applied here. This output goes to the input of the next flip flop, and this input goes to the next flip flop input. So in this way, shifting is achieved, and this output goes to the output pin. So serial shift with the control, we have input, which is one input, which is the serial in, and the control and the clock output and the serial output. And if we want a shift register to give parallel output also, so we will have 4 output pins for parallel out. Now rotate register, if we are connecting this output to this input, that means we are like shift right, but the leftmost bit, instead of filling with the shift in or value, we are filling it with the rightmost bit. So this is like serial transfer. So here we are giving that rotate register. Now shift control, whenever it is 0, it is the retain operation. So in this place, it will performing the shift operation. Now we have already seen the circuit for the full adder. So full adder, if you want to say n bit full adder, we wanted n bit to be connected in serial. Now if you observe that at one time, this is performing the operation. So this gave say C1 carry out. Then this started performing. This will be remaining ideal. So at that time, only one full adder is going to perform and give the useful result. So it is serial but requires n full adder. So for that, can we reduce it to just a single full adder? But we need shift registers to store as well as give input. So say we have an input for A and B, and finally we are modifying this content of this register to store the output value. So we got A and B value bit by bit. It performs one bit addition. It gives an output which is getting stored here, one bit. Then next this carry input comes here, the previous carry. That carry is added to the scene of this one. So we need a 1 cycle delay. So we have a D flip flop. Now we want to apply the clock. When this will be shifting, whenever the clock is enabled, when the clock will be enabled, when the shift control is enabled, as well as we get the clock. So in this way, we can perform the n bit A plus B using a one full adder. So universal shift registers. Okay, in a shift register, we want to have 4 operations: parallel in, parallel out, serial in, serial out, serial in, parallel out, and parallel in, serial out. So we have a serial input, we have serial output, and we have a parallel input, we have a parallel output. So in this way, we can like designing to perform all the 4 operations. So what will be the internal circuitry? So for that, we need all the 4 inputs, which is the uh, serial input, and okay, serial input is coming here. So if this is the serial input, then this output should be connected here. And if it is a retain state, it should be retaining it here. And parallel, it should be coming from here. And if you want to shift it from this side, if it is connected here, then this S2 should get this output. So in this way, left shift, left right shift, and then no change parallel. So here it is like I2, we saw it is performing this left shift, and we observe the I3 is performing serial in, sorry, parallel in, and I0 is performing no change, and I1 is performing right shift. So in this way, we are able to get all the 4 different operations. So example, like detailed representation with 0 0, it is no change. That means we have a feedback. And 0 1, which is the right shift, so we have to go from this direction. That is input flows from here, and this output is connected here. Output, input. So in this way, we get the serial shift. And left shift input will be applied from here, and 1 bit data getting shifted in this direction. And 1 1, which is the parallel shifting, so we get the input applied directly here, and which is coming to the parallel out. Okay, so before going to the Verilog code, you have any doubts? Y series shift means? I didn't get your question. You are asking what will be the requirement for shifting in serial? Okay. Is your question that why we need a serial shift or why we need a parallel shift? Okay. So, for example, we have an hardware which is requires just 1 bit data. And in that case, an input is also, now in this case, if we have an input, we have a bus of say 4 bit, then that means we will be using a parallel in serial out. Our input is at output 1 bit. Yeah, 1 bit means it is a serial shift. For example, if we have just input to be 1 bit, then it will be serial input, serial output. So we need like this two type of shift registers in order to use a single bit full adder, full adder, which is going to add three 1 bit numbers, one carry and two 1 bit numbers. So in this way, this shift registers are useful, and some of the other applications are given here. Why D means, the question is like why D flip flop alone? Because D is the data flip flop which gives the output to be the same as the input after one clock cycle. That is the shifting operation. The D, the next state, if it is 0, it gives 0 after one clock cycle. 1, it gives 1 after one clock cycle. And we want shifting. Whatever here, I want this 4-bit data. For example, if this is the data, I want this data to be applied here, not a toggle or anything. So the option is D flip flop or any other flip flop converted to D flip flop. SR should be converted to D because SR we have other options of also, right? So if 0 0, it will perform the QNs in SR. That means this state is useful for us. But if you apply this, then it will be performing a reset operation. And if it is this, then it will be performing a set operation. For us, the input is, we have a block which is where we get an input, say completely this 100, but output we want 1 by 1s because it's 1 bit. And we want output to be like 0 for one first clock cycle, next clock cycle 1, next clock cycle 0, next clock cycle 1. And this can be obtained only if we use D flip flop. Uh, is it clear? Okay, what happens for HA? Uh, okay, so you are asking like instead of this full adder, you want to use an half adder? Then this carry we cannot add. It will be performing like if I have this. This is my addition. 0 plus 0, 0. Half adder is sufficient. 1 plus 1 gives 0, 1. But if you have half adder, it will be just performing 0 plus 0. This one to add, we need another half adder or like that's why we go for full adder. That previous carry we store in a D and bring it here. Yeah, in half adder there is no carry. The difference between full adder and half adder is half adder the inputs are A and B. And for full adder we have the inputs A, B and C in carry. So this, if we don't want this carry propagation, if these results are fine, then we can go with the half adder. Half adder will give one result here. Carry out is there in half adder, but not the carry in. Why two shift registers? So, okay, we wanted this data, say which is A. Then for B, we need another shift register. And output it is coming 1 bit at a time. And if the output is also a 4-bit output, or like if you want to store and see somewhere all the output together, then again we can shift in here so that we can reuse this A register to store the output also. We have two inputs, so we need a two shift register. And carry is just a single bit, so of one flip flop is enough. No need of a register, right? Clear? Three inputs, then the full adder will have some other variation. Let us, if we assume that we have a circuit which we want to use it for multiple bits, say some comparator which compares between three inputs, say A, B, and C. This is a 1-bit comparator and we want to make it n bit, then we need three shift registers. See, the main idea of using a shift register here is that, see, uh, the idea was here was we have 1 bit A0, B0, C0. We performed the addition, then it gave C1. Then only we were able to perform A1, B1, C1. So if at this, if it is performed at t is equal to 0, we need to perform this at t is equal to 1. So this data we wanted to come serially, like B0 after one cycle B1, after one cycle B2. So we needed two shift register for this, and we needed this output should come here so that we will have the this feedback and it will perform. So in this way only we were like making the ripple carry adder. We felt like anyway we are going sequentially only. So why you can we use a single full adder? Is it clear now? Clock and shift control are different. Yeah, shift control means do you want to retain the state or do you want to shift? See, here it is shift control, which means if I'm giving one, I will be performing the serial in and the shifting operation. If I'm giving this to be 0, then I will be performing the retention of the state. I don't want to perform any shifting, I will just retain the state. And we need a clock separately. Yeah, both are different. Okay, sequential is serial. It's like at t is equal to 0, we have set of A0, B0, C0. At t is equal to 1, it operates on the next set of values. It is proceeding sequentially. So we can say to analyze any sequential circuit, we have to perform times expansion. So this is like expanding in the time. So this will be performed at t is equal to 2. T is equal to 2 means in the next clock cycle. So this is a kind of sequential or a serial operation. This adder is also called a serial adder because it's when you perform parallel, you need parallel full adders. And if there is a data dependency, then parallel, if you have a parallel adder also, it will be performing serially only. Like here, there is a dependency of this full adder for this C1. So anyway, it is going to wait and perform serial only, even though we have the hardware. Carry out and carry in is different. Yeah, carry in is the initial carry, and this carry we have to add, right? Full adder functions. If I take this as the full adder, the first full adder performs this one, and we have a carry in. So say if it is 0, so 0 plus 1, which is 0, 1. This is the carry in for the next step. So now only this full adder can start its operation. So 1 plus 1 is 1, 1. And this carry, again 1, and this carry. So it's 1. So I hope you understood what is carry. Here we mean the carry input and the propagation carry. And here we have 0, no carry. So this is the carry, final carry out. What is C in this example? C in. This one is the C0. This is just a 1-bit representation. So here if you see in the sequentially, we have this as the C input. So this full adder, say initially it is giving 0. So 0 will be this input. In the next state it will give 0 and it will come here. For example, we reset this to 0. Then the adder will be getting all 0 inputs. Then the output will be 0, 0. And the Cn carries the first C0 will be 0. The next C1 will be the first stage full adder output. Yeah, okay. So Verilog code for the register. So we have the so, uh, I hope your doubt is clear, right? The first Cn will be like in here, it's just the feedback, so it will be the 0, because if we clear this flip flop and begin, we will have a 0 for the first. The C1, that is the C0, C1 will be the value which is coming from here, will go here. It's an going to perform addition only. C in carry low. C0 is initial. That is the Cn. Like, yeah, this carry, if we consider, this will be 0 if we reset the flip flop, and this will come from the feedback of the flip flop. C0 is the initial. And this is just a block level representation, so it consists of C1 everything. So Verilog code for this, again we have the 4 operations like left shift, right shift, left shift, and retaining and parallel load. And this is the concatenation operation, which will be like combining this bit and this. And yeah, so this is the parallel in parallel out, means we have parallel input and the parallel output. And one, this is for sorry, this output is given input here for retaining the state. And we have something called tri-state buffers, which one of if it is 1, this is 1, then this will have a connection, otherwise this connection will be disconnected. That means either it will be connected to S or RW. So I think this will go for the previous year assignment questions. How many gates are in the positive edge triggered D flip flop? So it's the positive edge D flip flop, master slave combination. So it consists of 2 NOT gate, 4 NOR gate, so 4 NOR gate, 4 AND gate, and 2 NOT gate. So the master slave configuration, 4 NOR gate, 4 AND gate, 2 NOT gate. The next question, what is the characteristic equation of a T flip flop? So yeah, this we know that T Q plus 0 1 Q Q bar. So when T is 0, output is Q, or when T is 1, output is Q bar. So this is the Q plus characteristic equation. So T Q bar T bar Q. Okay, next question, difference between latch and flip flop. So we know that latches is level sensitive and flip flop are edge sensitive. So latches are level sensitive and flip flops are edge sensitive. Okay, next question. What is the value of JK input required for output to change from? We want 0 to 1. So it will go to 1 if it is in the set state. Set means it is 1 0, and it is toggling. Okay, level means if this is the clock, if my flip-flop operates in this region, if it is latch, if it is my D latch, the output, whatever is the input, or say SR, if it is 0, 0, S is equal to 0, R is equal to 0, output retains a state in this particular region. No, that is called level sensitive. This is a level. And edges, this is the edge. Okay, so, and one more input combination where it will go from 0 to 1, it is like toggle. Toggle is 1, 0, 1, 1. So it is 1x. Next question, when n is flip flop in normal mode. That is when it is not given active low or high. So we assume that when both preset and clear are 1, then it is going to perform the preset or clear operation. And if it is 0, then it is going to perform the normal operation. So preset and clear are low. And number of flip-flops required to construct an 8-bit shift register. So we need 8 bits. So it should have 8 flip-flops. Now determine the multiplexer size required for 8-bit 4-function universal shift register. So 8-bit, that means we need 8 multiplexers. And it has 4 functions. So it should be 4:1 mux. So it is 8 4:1 multiplexer. Next, which flip-flop avoids receiving the input of 1 1 in an SR flip-flop? So we in SR 1 1 was not allowed. So in JK 1 1 is used for the toggle. Next, which flip-flop do we get when we combine JK input of the JK flip-flop? So we get a toggle flip-flop. Okay, so the next question. Okay, so okay, we will try one flip-flop conversion. We have some more time. So if you want to convert JK flip-flop to D flip-flop, so here flip-flop which is available is JK, and the required flip-flop is D. So for the required flip-flop, we write the characteristic table, and for the JK flip-flop, we write the excitation table. So we have D flip-flop. So what will be the Qn plus 1? 0 0. sorry. And if it's a previous state was this. Next state will depend just on the D. So we get this output. Next, using this Q and Qn plus 1, we have to write Jn. So it is the, this was the characteristic table, and now this is the excitation table part. So we have the values for J and K. So now we have to draw the K map to simplify. So Qn and D 0 1 0 1. That is 0x 1x. That means this we wrote for J. So J is equal to D. Next Qn D. So 0 1 0 1 x x 1 0. So this means K is equal to J. So the JK flip flop Q bar. So this is the D input. Complementary value goes here. This is the clock. Okay, so any doubts? Even SR in place of JK. This table, there may be some changes. Actually, we are not using SR because that 1 state is not allowed. So at least in we remove that and make that 1 state to toggle in JK flip flop. Otherwise, SR and JK for the other three combination it remains the same. Yeah, JK we have 1 state where it will perform the toggle operation, but SR that 1 state is forbidden because it was giving an unstable output if we assume both the gate delay are equal and input arrives at the same time, and it causes a race condition if one of the gate is faster or one of the input arrives before. So that race condition and the unstable condition is removed. That because of that, that input was not allowed in the SR flip flop, but it is allowed in JK. And because of this, in JK we have that feedback, right? So that makes the JK flip flop to operate as a toggle flip flop when J is equal to 1, K is equal to 1. Yeah. So any other doubts? Last problem 1x in JK. Can you explain again? Okay, yeah. 1 second. Yes, for JK we have this flip flop feedback, and here we don't have that. 1 state is allowed. So here, if you see 1 state, it gives complementary output. Okay. Next question number 1. Okay. I think this question. Yeah, 1x We want the output to change from 0 to 1. When this will happen, if 1 means it is either set operation is happening or it is a toggle operation. And when it is set, the combination of input is 1 0, and for toggle it is 1 1. So 1, and whatever is this input, if we apply, it will be output will be going from 0 to 1. Is it clear? Okay, so any other doubts? I think this textbook, before every NPTEL start itself, they are providing the name of the book from which it is taken, right? Like if this is the lecture, it is. Yeah, I think for every class, it is given the starting slide from which book is this referred. Yeah, I don't know about sequential, but yeah, combinational, I remember seeing. Yeah, this book. I think before starting of every class, book name they have mentioned in the chapter. You can refer to that. Otherwise, uh, or this is one of the author name. This also you can refer. I think any addition should be fine. And if you are that is like digital design, and if you are looking for something with respect to VHDL coding, which is like you can read this book. Okay, so any other doubts? Yeah. If no doubts, then can we end the today's session? Yes. Anything else? Okay. Yeah. Thank you so much. So I will end this session.